Okay, in the previous class, what we discussed was hierarchical clustering, correct? Moreover, hierarchical agglomerative clustering. The idea behind the clustering this clustering technique is that you start your clustering procedure with every cluster being one point, right? That's it, very simple. Okay, and then on the next iteration, you're finding the two closest points and merge them into one cluster, right? So therefore, total number of clusters is reduced by 1, right? And on the next iteration, you again measure the distances between all points and the newly formed cluster, find the smallest, and then do the merge, right? So on each iteration, the number of points that stand by themselves is reduced by 1 every time, right? Some clusters can merge on the way, and the final output is that all of your points are grouped into one big cluster, mega cluster, right? So let's reproduce the same analysis right now, okay? So open up Tableau, no, not Tableau, Jump, right? And the file utilities, right? That's the one that we used, okay? Alrighty, so let's use the same exact procedure as we did before, okay? So I go to Analyze menu, and then clustering analysis, and then hierarchical clustering. And let's use, for example, well, average, right? We used centroid, I believe, for the previous one, right? How do you measure distance between clusters? You take center of gravity for each cluster, find the mean point, right? Average point, central point. And basically, after, that's why it's called centroid. And after that, distance between two centroids is essentially distance between two clusters. That's what we use. But this time around, let's use average. Average is kind of different a little bit, right? In what way? In order to find distance between two clusters, we have to take all points from cluster 1, all points from cluster 2, measure each pairwise distance, right? However many of them have. And then calculate the average out of all these possible distances between point in cluster 1 and point in cluster 2. So let's use average, just for the heck of it. Just let's see that maybe our clusters will form differently. Okay, so I'm going to select all the columns, right? So these are all the variables that I'm going to take into consideration when forming my clusters, when calculating distances, right? And just add them to the columns. And after that, I'm just going to click OK. And here is Dendrogram, right? Dendrogram essentially tells me how the clusters are merging together, right? And note that this time around, you see that method equals the average. My clustering is different, right? Just for comparison, let me do the same exact thing, but when I'm using not the average distance between clusters, but centroid instead of that. And kind of let's compare them side by side just to see if they differ, right? So I'm going to run the same exact procedure. Let's do that. Clustering, hierarchical. I'm going to use centroid and do the same exact thing, right? All the variables, and click OK, and there it is. Okay. Now I want to put them side by side and kind of to see and compare if the clusters are different, right? So this is my analysis number 1 with centroid. And that's my analysis number 2. Can I show them simultaneously? I'm curious. Or is it one or the other? No, here, right? Okay, so here are my two clustering procedures, right? Okay, do you see any differences between them? Or are there any differences? Well, there are differences, right? For one, for example, if I'm using centroid, look at that. The very last cluster to join finally the big mega cluster of all points in one, right? If I'm using centroid, that would be this company right there, right? What's that? San Diego, right? So up until the very end, the San Diego utility power company stands by itself, right? All other points join together, you can see that, right? So all other points join together, but San Diego joins the game only the last one, right? So it stands out by itself up until the very end. Here, if I'm using the average method, it's not quite like that, right? Look at that. The last cluster to join the game, so here, right? When I have two clusters at the end, this is one big mega cluster, right? And this is, well, smaller cluster, but it's not just one, right? It's formed by Idaho, Puget, and Nevada, right? They form their cluster. And then it's the last cluster to join, right? So what does that tell us? That tells us that if you use a different method to calculate the distance, your clustering will be different, right? So natural question is, which one is better, right? How do you judge? Or even more general question. Since every time when I use different distance, my clustering is going to be different, then what really am I looking for, right? How do I judge whether or not I have good clustering versus bad clustering? Well, here is the idea, okay? Number one is clusters. Remember we discussed that in the previous class. What happens if I go to the extreme? All points are in one mega cluster. Is that a good result for me? Like my entire data set is just one big cluster. No, right? It doesn't really tell me anything. So remember, the idea behind clustering is that I want to take all of my records and break them down into the groups, and each group looks very similar to each other. Points, right? In each group, they look very similar to each other. Because I can treat them as one group and do the separate analysis for it, right? For example, run linear regression just for this cluster, or do the classification tree, or do the logistic regression. Because these things look similar, I'm supposed to get better results, right? After I run my analysis, my model on just one cluster. And then I take second cluster and do the same thing. So I'm going to build multiple models, and each model will be applicable only to the cluster where it was built, right? Moreover, what happens, let's say, for example, I do that for customers, right? It helps, right, businesses in real life. Let's say I do this analysis for customers in marketing, right? I will group customers into groups or clusters that make similar purchases, right? Isn't that what marketing does? They look for patterns, right, in the customer's behavior, right? So if I go ahead and do that, if I take all of my customers' purchases and I'm going to split them into clusters, I'm going to group together similar transactions, right? And then after that, what I'm going to do is create a label for each group, right? Each cluster will be characterized by certain typical behavior, right? For example, all the people who bought lawnmowers, okay? Or all the people who shop, only on weekends, okay? So something, right? So in marketing, they call these groups personas, right? Or customer profiles, okay? And then next time when a new customer comes in, okay? So for example, let's say I'm a retailer, okay? And I found out that people who buy lawnmowers are the typical profile of these buyers is they're middle age, for example, between 35 to 45 years old, right? They own a house, they have a dog, they have they drive Toyota Camry, for example, something, right? Something that's common between them. Next customer comes in, completely new, right? Can I find out all this information about a new customer? Where they live, whether or not they own their house or are they renting, what kind of education they have. I can find this information. It's for sale, right? The biggest company you never heard of. Have you heard about biggest company you never heard of? I believe it's called Axiom. That's basically what they do. They sell customers' information. So your information is out there for sale. They collect information about people from different sources, and then if other organizations want to use that information, they just sell it to them, okay? Biggest company you never heard of, so to speak. So next customer comes into the door, I can find out all demographics about that person, right? And now I have all of my clusters, right? Based on my previous analysis. What I can do is I can say, well, where does that customer belong, right? Into which cluster? So I can essentially go ahead and compare the demographic of that specific buyer to typical demographics, to the characteristics of my clusters, and say, hey, look, he belongs to cluster number 3, and therefore here are the typical transactions that these people do. Therefore I can market some items in a more intelligent and educated way towards that specific buyer, right? So that's essentially how that can be used. So this example illustrates to you that clustering, there is more than one way to do the clustering, right? And every time when you do clustering, your results probably will be different, okay? So what are we looking for? Well, one thing is interpretability. So let's take one of these things. I don't know, average, for example, or centroid. Let's close this one and let's stick with centroid, right? Right now I am, and you remember, right, that I can move this diamond in and out, right, and therefore pick different number of clusters, right? So the largest number, of course, is all points. It's just a cluster of 1 point, 22 of them, right? Another extreme is this one. Probably I don't want to go with either extreme, right? I don't want to group all points together, all of them, and I don't want to ungroup all points, right? That also doesn't give me any data. So I should pick a reasonable number in between. Let's say, just for the heck of it, it's number 3, right? So, or number 6. Let's do number 6. So, what are some of the considerations that companies should employ in picking what number of clusters to select? Well, one consideration is how many clusters you can handle. Let's say that this is a marketing example, okay? Where my marketing says, I want to take all of my transactions performed by buyers, okay? And split them into groups of similar transactions. But here is one limitation. At the end, I want to create a separate marketing pitch for each group, for each cluster, right? But because I have limitations, I have so many people working for me, right? I cannot handle more than 4 groups or more than 5 groups, right? That's it. So that means that 6, 7, 8, 10, don't do it, right? That's the message that they're communicating to you. So number 1 is how many clusters you realistically can handle for whatever purposes you're creating clusters, right? That's number 1. Number 2 is, do I want clusters that are kind of overlapping with each other? In other words, I can classify people either to cluster 1 or cluster 2 because these are very close. No, I don't want that, right? Because if clusters are very similar, if their centers, so to speak, right, are very close to each other, how do I distinguish them, right? Is it cluster 1 or cluster 2? It's kind of a toss, right? So if clusters are not separated enough, they are not far away enough from each other, that's also a bad clustering technique, right? Really what I want to do is group observations, group my data points into clusters so that they really kind of stand out separately from each other, right? Make sense? Also, what will help me is if I would be able to find certain characteristics of each cluster that kind of stand out and separate that specific cluster from others. Here's what I mean, okay? Let's do some visual analysis with this one, right? So I use centroid method for this clustering technique. Now let's go to the right triangle menu and let's do the, oh god, I believe it's supposed to be called parallel plot. Do you see parallel plot somewhere here? Constellation plot is one thing.
Parallel coordinate plot at the bottom.
At the bottom? Yeah, parallel coordinate plot, right? There you go. Okay. Parallel coordinate plot. Well, is there another one? Let's take a look. Scatter plot. Well, let's take a look at cluster summary as well. Okay, cluster summary. So I remember what I did is I said I'm going to stick with 6 clusters, right? Okay. I'm going to stick with 6 clusters right there, okay? And all of these numbers, they basically characterize each of my clusters, okay? So, for example, cluster number 1. Let me click on cluster number 1, and there it is, okay? So it highlights for me the first cluster out of 6 that I've picked, okay? It says all of these observations, all of them have certain numerical measures, right? Remember, we compared them, we said that we're going to use these 8 columns, right? The ratio of the debt versus assets, right? Then return, rate of return, right? The cost of the fuel cost of generating 1 kilowatt, then sales, percentage of nuclear, etc., right? So we used 8 different things to characterize our data points, okay? So these numbers essentially represent the averages, okay? So they tell you essentially cluster number 1, for example, has an average of 1.17. Okay, as far as this first column is concerned, fixed. So if I take all of these numbers, all of these companies grouped together, and average out their fixed values right there, then I'll get 1.17. Right? So you can see that it's all over the place, right? Okay, so cluster summary. Which one did we look at? Parallel coordinate plot, right? This one. That's not quite what I'm looking for, to be honest. I was looking for, let's see, Dendrogram? No. Well, let's take a look at the parallel coordinate plot. I don't know why I can't find this thing right now, quite honestly. Okay, so what it does for me, essentially, what I was looking for is put 6 clusters on the same plot, essentially. So all these averages here, right? All these averages, for each cluster I computed the averages for all the dimensions, right? All the variables. So if I put them on the same plot simultaneously, I can kind of visually see how clusters are different from each other, right? So right now what I have is the plot of all of my 6 clusters, right? So for example, cluster number 6, here I select the cluster number 6, and where's my parallel plot? Parallel plot is right there. Here's my cluster number 6. You can see how basically it goes, right? How the averages develop. So what I was looking for is the plot that puts all these averages together in one place. Parallel plot. Let's see if I can find it. Scatter plot matrix. No, that's not it. Pivot. No, that's not it. Dendrogram. Okay, so I'll show it to you next class. I'll find out how to bring it up and show you to the next in the next class. Okay. So today we're going to discuss yet another way how we can cluster observations. Okay. But before we do that, let's discuss what's the downside of the agglomerative clustering technique. Here's the downside, ladies and gentlemen. Okay. Let me bring up a new page. What we had in our example was data set with how many observations? 22, right? 22 observations. So, on my first iteration, what I need to do is compute distances from each point to each other point. Agree? Right? So, if I pick, for example, point number 1 out of 22, how many distances is that? If I pick point number 1, how many distances do I compute for the point number 1? 21 distance, right? From that point to every other point, right? Now I can exclude that because it's done. Now I pick another point from the remaining points. How many distances do I need to compute for that one? 20, right? Because for the first point, it's already computed, right? Plus 20, right? Okay, that's done. Then I take point number 3. How many distances? 19, right? 19 plus, and the last one is going to be when I excluded all points except the 2, right? That's going to be 1 distance, right? Oh God. How much is that, by the way? Let's see if you remember. How do I add consecutive numbers together? That's not quite factorial. That would be factorial if they're multiplied, right? That would be factorial. But thank God it's not a factorial, right? It's plus. You want to hear a funny story? How many of you heard about German mathematician Carl Gauss? You heard about him? Yeah. Yeah, Carl Gauss, what's he famous for? That's what he's famous for. What's this? It's a graph of what? Of normal distribution, right? The person who proposed normal distribution was Carl Gauss. I believe he lived, it was either 16th or 17th century, okay? So sometimes normal distribution, also called Gaussian distribution, okay? in the honor of Carl Gauss. Okay, so the funny story basically is when Gauss was in high school, or whatever school was in 17th century, right? Their math teacher wanted, to give students in class a really difficult problem to figure out, so that they, shut up and don't annoy him. So he said, add for me numbers from 1 all the way up to 100. So people went down with this thing. How long will it take you to add together all numbers from 1 to 100? A long time, right? If you do it just like that. 1 plus 2 is 3 plus 3 is 6 plus 4 is 10, etc., etc., right? That'll take you probably 20 minutes, 40 minutes, right? Gauss was done in like about 1 minute after that. So here's what he did. He said, well, let's call it a sum, right? Okay. And let's do sum, but in the reversed order. So what if we record it like that? 100 plus 99 plus, and here's going to be plus 1, right? So now I'm going to add right sides together. That's going to be 2s. And on the left side, what I'm going to have, 100 and plus 1 is 101, right? 99 plus 2 is 101, right? Next one is 3 and 98. How much is that? 101. So the last one is going to be 101. And how many of these things you're going to have? You're going to have 100 of them, right? So therefore, really, all you have to do is take 100 multiplied by 101 and divide by 2. And that's going to be your sum, right? So therefore, if you need to add n numbers together, really the formula is, n plus 1, right, times n, sum, right, divided by 2. Okay? So if you need to add 100 numbers, that's going to be 101 times 100 divided by 2. Okay? So same exact thing right here. Okay? We need to add, if I want to use my really small data set, which contains 22 points, right? How many distances do I compute on my very first iteration? Well, 22 times 21 divided by 2, right? So therefore, it's going to be 11. So the answer is going to be 221, I believe, right? So on the very first iteration, when you're computing distances between just the points, and you have 22 points only, you need to compute 221 distances. Is that a lot? No, not a lot. For a computer, it's not a lot, okay? But that's a small data set, right? What if your data set contains, let's say, realistic, right, data set? How many points are we looking for at the realistic data set? Let's say 1 million. 1 million is not a big data set, by the way, okay? It's actually pretty small. So 1 million points, okay? So how many distances are you going to compute in the very first iteration? That multiplied by 1,000,001, right? Divided by 2. So we're talking trillions probably, right? Is that going to take a long time? You bet it's going to take a long time. So do you see where the inefficiency of this method is coming from? This method is actually pretty cool, okay? The hierarchical. We're talking still about hierarchical method, right? It is pretty cool, no question about that. The downside is, if you are dealing with a large data set, here's the downside, okay? It's going to take a long time. The algorithm is going to run slowly, right? And every time when you compute a distance, you need to record that somewhere, right? So you need to store 1 trillion or whatever the number is, computed distances, right? Is that cool? No, right? You need a big storage. You need a lot of time, right? So therefore, this algorithm is not working well for large data sets. That's basically the point that I'm trying to bring across. Do you see that? A lot of distances are being computed, right? They have to be stored, they have to be compared against each other, we have to find the minimum. That will take a long time, it'll take a large storage, okay? Plus another downside of this method is, once the point joins some cluster, can it join some other cluster? No, right? The points are being basically consumed by clusters, right? Clusters grow bigger and bigger and bigger, and once the point was assigned to one cluster, that's it, there is no getting out, right? If we assign the problem incorrectly for some reason, it doesn't go backwards, right? It's only forward algorithm. It eats more points. Clusters eat more points. They become bigger, right? There is no way of getting out, okay? So therefore, here is another clustering method, y'all. Okay, so let's take a look at something that's called, okay, not this one, okay? K-means. K-means. K-means is another clustering technique which is much more friendly in terms of computational requirements, okay? It does not require quite as many computations as the hierarchical clustering. And the idea behind the K-means is that from the get-go, somehow I need to decide how many clusters to have, okay? And then that's exactly how many clusters I'm going to end up with, okay? So if I decide 3, it's going to be 3 at the end. If I decide 5, it's going to be 5 at the end. So this number I have to tell the procedure right off the bat, okay? So here what I did is I created this example. Let's say that we have how many points? 4, 4, and 3, 11. 11 points, right? How many clusters do I have in your subjective opinion? No, 11, that's my starting point for the hierarchical technique, right? But forget about hierarchical clustering. You look at the picture and tell me how many clusters do you see? 3, right? Obviously. That's one, that's another one, and that's another one. So let's say that I want to start this procedure under the explicit assumption that, I'm going to end up with k equals to 3 clusters, okay? That's why it's called k-means, okay? I'm going to end up with k clusters, whatever number k I decided. And what the procedure does is it says, let's start with just 3 points, fairly randomly selected, okay? So let's say that this is going to be my center of the cluster. You know what? I'm going to change to the red right there, okay? So let's say that this is going to be my center of the cluster number 1. This is going to be the center for the cluster number 2. And somewhere over here, I'm going to be having the center of the cluster number 3. Well, you tell me, did I pick the good values for my centers of clusters right now? No, I didn't, right? Completely screwed up, right? Probably should be in the center of these agglomerations, right? But that's my starting point. What do I do after that? After that, I measure the distances from each point to each cluster, okay? And I assign the point to the one which is what? Closest, right? So, say for example point number 1, right? This one right here. So this is the distance for the cluster 1, for this center, and for this center. Which one is shortest? I think this one right here, right? So therefore, let's say that this is going to be cluster 1, and this point is assigned to cluster 1. And I do the same thing exactly with the rest of them, right? So this point right here, distance 1, distance 2, distance 3. I think this one is shortest, right? So therefore, let's call it 2, and I'm going to assign that to cluster number 2, okay? And I keep doing that. So that point probably becomes point number 2, agree? It's closest, right? That point right here is going, that's 3, that point is going to be 3. That point, I'm thinking it's 3 as well, right? That point, I think it's 1, right? It's closer to 1. That point right here, what do you think? It's kind of a toss, right? A little bit. What do you think? 2 or 3? 2? Okay. So let's say it's 2 as well. Okay. All right. How about this one? That's a 3, right? That's a 3. Okay. And that one is, I'd say 2 as well, right? That one is 2. And we're missing a few, right? So this one, again, it's a toss. So what do you think? 1 or 2? 2? Okay, so that one is 2. And that one is 2, right? Okay, cool. So, there you go. My very first iteration, and the procedure goes in iterations, okay? So, I'm going to show you that it will eventually come to the point where the centers are going to be exactly in my centers of clusters, okay? So, but right now, here is how I think my my clusters are split. So, these are all the ones, right? So, hold on. This is my cluster number 1, right? These things right here are my, what, cluster number 2, agree? Okay. These things right here is my, no. These things right here is my cluster number 3. Correct? Okay. So now what do? Now I will, because clusters now contain points, right? So I want to find what? For each cluster, I will find what makes sense. Center, right? Because there are points, so I can find the center. So this cluster number 1 center is somewhere here, agree? That would be cluster 1. Cluster 2, maybe it will move a little bit. Let's say that it moves somewhere over here, okay? So that's the center for cluster 2. And cluster 3 moves probably somewhere closer to these 2 dots, right? Because it's the center of gravity. So that probably is going to be the center of my cluster 3, right? It has 3 points, but this one is kind of far away. So the other 2 points, they kind of pull the center towards themselves, right? And after that, what I do is, now I have updated my cluster centers, right? So after that, I'm going to recompute the distances between all points and my new clusters again, okay? So here, right, for this point, I believe it's still 1, right? So this one is still 1. Number 2, probably it's still 2, right? So let's leave it at 2. This number 2 right here, okay? It's kind of a tough call, right? Let's say that 1 is closer, okay? So 1 over here. This one I believe is still 2, right? 2 is closer. Okay, cool. So now 2 and 3. Well, I'm guessing 2 is shorter. So this one is shorter, so it's still a 2. This one is still a 2, I believe. This one is still a 2. How about this one, 3? I believe this is shorter now, right? So this label is shorter. So therefore, I'm going to still label it as a 3. Okay. And this point right here is still a 3, I believe. Right? This point right here is still a 3. Okay. So now I have updated my clusters, but what happened is really nothing changed except that is my new cluster number 1, right? Okay. And then what happens after that? The center of cluster number 1 moves somewhere over here, right? It's closer to the 2 points right now. Okay. So this is my new center. And now when I recompute the distances, guess what will happen? This point number 2 is going to be closer to cluster 1 now, right? So I'm going to label it as 1. This one is probably also closer to cluster number 1, so I'm going to label that one as 1, okay? And everything else stays the same pretty much, right? Well, except that point, let's see. This one, this point belongs now to cluster number what? To cluster number 3, agree? So this one becomes a 3. So now I have to update my clusters again, right? So 1 actually is this constellation right now. 3 also changed, right? 3 now is that. Hold on. 3 now is this constellation, and 2 is this one right here. Okay. So now I recompute the distances again. So guess what? Center of the cluster number 1 is going to be somewhere right in the middle, agree? Of this group. Now cluster number 2 starts to look like actually cluster of close points. So therefore center is going to be somewhere over here. And cluster number 3, I believe, it's the gravity, right? Between 3 points and 1 point. Where the center moves? Closer to 3 points, right? So therefore the center moves over here somewhere. And that becomes cluster 3. And now I recompute the distances again. So obviously, is that obvious that all the points that are cluster 1, the closest point is the cluster 1 for them? Yep. So that one doesn't change, right? It remains the same. Now over here, from this point, here's the center for the cluster 2, and here is the center for the cluster 3. So what do? I move that point, and it becomes part of cluster number 2, right? So therefore, at the end, here's what happens, right? When the procedure, so the procedure goes basically in iterations, right? So here the center is going to be somewhere, I don't know, somewhere over here. Okay? So the procedure goes in iterations, and at the end, basically, when all points stop moving, so after that, if I run this procedure again, will any of the points be reassigned? No, right? Because these points are closest to the center of cluster 3. Same applies to clusters 1 and clusters 2, right? So points basically stop moving after that. So once these points stop moving, or there is very slight improvement, there can be a point jumping between two clusters back and forth. That's where I have to stop, right? And I have to say, well, this is it. Okay, I reached the end, and therefore that's my division of points into the clusters. Okay, so let's take a look at how this is done in jump using the same exact example as we did before. Okay, so let's go back to utilities. We go through analyze menu, right? Clustering, and then after that we did hierarchical, right? And after that, what we have to do is go to the k-means, right there. And it's the same dialogue, right? So I'm going to say all of these are going to be my dimensions, the variables that I'm using to cluster points, right? Just like that. But remember what k-means stands for? I need to provide the number k, right? I need to tell the program how many clusters I want at the end of the day. So therefore, there should be some place where I enter that number, right? And when I click OK, there it is. Okay, it says number of clusters that you want. Default is 3. Well, let's say 5, right? I want 5 clusters. Okay, and then I click on the Go button, and there it is. Okay, it gave me 5 clusters, and I can even see. Let's take a look. See, I believe I don't get the dendrogram. Let's see. Does it give me the dendrogram? No, it doesn't, right? Okay. Iterative clustering. What about, no, I don't have a dendrogram, right? Okay, but I do have parallel coordinate plots, right? Well, we try to interpret that. It doesn't interpret nicely, right? So I think we're done for today. In the next class, I'm going to show you how to basically take a look at the parallel, it's called parallel plot. Okay, so it basically shows you how the clusters are different on all these dimensions, like these 8 different columns that we have selected. And then after that, we can start naming the clusters. This one is, for example, high percentage of nuclear power. This one is high sales. This one is low cost cluster, etc., etc. Okay. All right. So this is it for today, and the projects are due tomorrow by 11:59.